thank you all for coming. Let's continue with where we left off on Tuesday. We were just starting to get into the mechanics of CUDA, and we'll do it a couple different ways, as we also kind of parlay that into discussing some of the microarchitectural aspects as well. We'll just do it by example to begin with, and I think that's not a bad way to start. And then as we add more complex functionality, we'll kind of just add onto the examples. So this is essentially where we left off on Tuesday. This was our first CUDA kernel that was necessarily not doing anything because it has some hidden functionality here, but we're just looking at what made this different from a traditional C or C++ function call. Syntactically, it looks fairly similar. Some of that is just syntactical additions to kind of specify this as a kernel function. The other things we saw were that generally, since all of this code is kind of written in the kernel from a single thread's perspective, the most common type of input to that kernel would be just a series of pointers. Each thread would then have access to basically the same base address to some object in memory, and then they would do some internal bookkeeping to determine from this base address what subset of this object am I, the individual thread or group of threads, responsible for. So while there isn't a ton of bookkeeping in this example here, there is a little bit of it where there is going to be some automatically assigned thread indices and unique ID information per thread, and usually at the very beginning of the kernel and oftentimes at the very end of the kernel, you have that bookkeeping logic that's determining, given my dimensional data of which thread I am amongst all the threads, carve out a piece of the work, and then read from the input based on that piece of the work, right to the output based on that piece of the work. The other example we then looked at was the vector add example, which, again, we haven't covered all of what this means, as we'll talk about a little bit more about it today, but it's doing something very similar. The previous example just had 2 pointers. This is taking 3 pointers for input A, input B, output C, and then a number of elements that we check to make sure we're not going past the end of the array. And it is doing some dimensional arithmetic to basically determine, given a dimension of the block and which index I am in that X dimension, calculate a unique index I, and take my word for it for now that this value I would be different for every single thread that gets executed, given how this kernel was launched in this particular application. Just a quick end of array sanity check is all that if statement is doing, and then each thing is just doing its individual work. Given that index, take A of I plus B of I, set to C of I.
I'm a little lost on the dimensionality of the indices.
And I haven't talked about it very well yet. So yes, I haven't talked about that. Other than we can kind of squint and see kind of what's happening here. This one I think we can see is just an X dimension, so it's a linear array. The other example, I was going to do this one here, just looking at it. I think we can also kind of squint at this one. That's our approach to learning in this course. We squint at code until it makes sense to us. But at least that's how I tend to learn things. One argument for that approach to learning is, every time there's some new technology, it is really just an evolution of something that's already existed before. So if you can put what's new in the context of what you previously knew, learning becomes a very straightforward kind of incremental process. So I haven't talked about what the indices mean, but I think we can figure it out, right? Just kind of squint at it a little bit. What do we think that example is doing here? Take a minute and think about it. There's no function call here. The actual math is kind of inherent in the just a single line of code we have here. What do we think this example is doing?
Adding numbers.
It is adding numbers.
Like adding to matrices?
Yeah, matrix addition is what I would call this example. Again, I haven't talked about how there's multiple dimensions to how you can lay out your threads here, but that's what .x and .y is looking like here. Take an X index for the thread to determine maybe the row of the matrix. We take the Y index of our thread to determine the column of the matrix we're interested in, and then consequently each thread would be responsible for one element in that matrix, adding the same location of A to the same location of B to store the results in the same location in C. Most of the interesting examples are going to be multi-dimensional in this way, and we can get up to 6 dimensions where it does get pretty hairy in terms of the bookkeeping required. But I think we can also get pretty far in our understanding with just 1 dimension and just start with that. You will find that here is where you do need like the CUDA programming guide alongside when you're programming, because knowing that for a single dimension, you're limited to this many number of threads, and then if you have multiple dimensions, there's these other limitations. That's all something you just have to have the guide in front of you because there's no point in memorizing it. It changes every iteration anyway. But even with just a single iteration, we can write parallel code and reasonably fast parallel code. And let's give it a try today to see what we can do. So my thought was, let's try to write a CUDA kernel that computes a Taylor series expansion for an array of input values. Do you guys remember Taylor series expansion? If not, then this is not going to go well. But arbitrary Taylor series expansion, I don't know why I picked something so mathy. I guess, you do enough vector addition, you want to try something different. But Taylor series expansion for the function e to the x is relatively straightforward, right? Because Taylor series expansion for e to the x is just the derivative is the same, right? The derivative of e to x is also just e to the x. So you can actually just instead calculate the value given an initial starting point and just run a certain number of iterations to get a value that should be reasonably close to correct here. We can do everything but like the final kernel and then see how we would have to add the kernel associated with it. It should be able to be done in a way that's very similar to the vector addition. It's not identical, but it should be fairly similar to the vector addition in that we would take an input array, a singular input array x, calculate a singular output array output, and we may want to have a separate constant for the number of iterations. So let's give it a try. And we can do it within vector add here. Instead of maybe breaking vector add, let's just create a separate kernel. And we could add comment. We don't need comments. No one's ever going to read this code. This is going to just be called Taylor. And at least based on what was on the slide, it's not called A, B, and C. It's called X and output. Nowhere here are you really specifying that something is an input or output. They're all just pointers, right? And that's true in C programming in general, right? You provide a pointer to a function. It is kind of both an input and an output in terms of the array of memory that it's potentially accessing. The previous kernel had a num elements to kind of check to make sure we weren't past the end of an array. We could also have that same if statement that wouldn't be wrong. I don't think there's any issue with going past the end of the array. So what we would probably care about is not num elements, but maybe like num iterations. How many times do we want each thread to calculate that next value of e to the x, or estimate that value of e to the x. All this code is going to have to get wiped out. That value of I, even though we haven't walked through all the thread bookkeeping code, probably can still be correct. And for now, we can just do something like output of I equals x of I. That's not correct, but at least it's something that will compile and give us a result that does something. As we've allocated, here we have allocated our input vector A and B and C. Now, let's call that H underscore is just kind of standing for like host side. That's just a naming convention. Host side X, it was lowercase x. Host size aside output. Check to see if the allocation, what are the odds that the memory allocations didn't work correctly. We need to initialize those values. In our case here, then we don't need to initialize output at all. We just need to initialize our value of x. And for doing our Taylor series expansion, again, I realize as I'm polling the class here, this isn't maybe a topic that's terribly interesting in terms of the actual math here that we're implementing here. Taylor series expansion tends to converge when it's around x equals 0. So we calculate it by the derivative, the value at that value of a divided by n factorial as we do the derivative to the nth time. We just kind of add all those individual terms. So we take f0 of a over 0 factorial times x minus a to the n, x minus 0 to the n, for 1, for 2, for 3, for 4. Tends to be stable when the value that we're interested in is around 0. So if we are doing this to calculate f of x equal to e to the x for a equals 0, then our values that we'd want to provide as inputs to do should be around the value of 0. So this code here that kind of randomly generates, for the vector add, this takes random numbers and divides by rand max. that gives us a set of values in the range 0 to 1. So that actually would also work. We should be stable around 0 on both dimensions. So we could do something like, start with negative 0.0 or 1.0, something like that. So as we iterate, we start at negative 1, then we go all the way to 1.0, and we kind of scale by that number of elements. So easier to debug than if it's truly random values and not knowing exactly what the value should be. So we allocate that. We also then need to allocate the corresponding array on the device. Here I am literally just kind of copy pasting and tweaking the code that's there. We do need to do then output. We don't need to be, but we do need our value for the output.
I have a quick question.
Sure.
It's more just C knowledge. Does that line, the h of x line, 1 minus or minus 1 plus that, does that just compile left to right then, assuming it'll do the 2 times I first before it divides, or how does that?
Order of operations is PEMDAS, right? Like you would have learned like back in the day. So it would be left to right. So 2.0 times I divided by num elements. C also promotes to float if there is a float there. So I could have cast to float, but you don't need to because it's 2.0. If it was just 2, that would not have worked correctly. But 2.0 promotes to float, and then you get a value of 2 divided by, what is that, 50,000. Then, 0 divided by 50,000, then 2 divided by 50,000, then 3 divided by 50, 6 divided by 50,000, then eventually 100,000 divided by 50,000, so that the maximum value would be 1.0. This approach of doing it randomly also is fine. It's going to be harder for us to debug when things go wrong here. Somewhere, something is not being declared. Let's see here. Float d underscore output equals none. So that part's okay. So we've allocated. We then have to do memcopy. And for now, because the variable types are the same, we're just going to make sure that we change everything that was listed as A to D. Syntax highlighter seems a little confused about what's going on here, but that should be okay. H underscore X is fine. We're going to launch. Now, we're not going to launch vector add. We're going to launch Taylor for the same dimensions, and that's going to be one input is D sub X, the other one is D output. And we could use num elements, but we now have num iterations. We'll just make it a constant 10. I don't actually know what the right number would be for a stable result. Finally, we are going to copy the results back now to the host side. And here we did a calculation to determine if the addition was correct. So we talked about how, from a performance perspective, this seems a little backwards, right? We do all this GPU code to launch things on the GPU, and then we go back and we run it all on the CPU anyway to confirm that the results are correct. Well, for verifying that it's still the correct thing to do, now what we should be checking is whether or not f absolute value, but whether f exponential of h sub x of I minus h sub output of I. If it's greater than some amount of value, we'll get some verification fail. So again, here we're manually calculating the result, e to the x on the CPU side, and we're checking if the result is within some range or not. We probably should do absolute value of that to see, okay, did I get within a reasonably close range of what the Taylor series expansion calculated? Because while the value of e to the x is going to be positive, the difference between the Taylor series and the correct, or what the math library calculation for e to the x gives us may in fact be different. And if any of those fail, we should get a test fail. So even if the logic isn't correct, it's always very important not to say, okay, does it compile at least? Compile first, worry about correctness later. It's much easier to change your hello world example that actually compiles than it is to go from something that doesn't compile to something that does compile. So we can fix functionality later. In the interim, this would be under vector add. D sub A, D sub B, D sub C. this is in the right direction. D sub A, D sub B, D sub C. Let's see if this is looking at the right file. Afterwards we free all the device memory. There was more. And I guess we can free the host side memory too, that's fine. I mean, the application's ending. Why free memory? Okay. And if we want to be really specific about like what our error messages will look like. FEXP is undefined. That's not a good sign. We'll go errors top, bottom, and find out what they are. Missing semicolon I could probably figure out. Line 48, expression must be a modifiable L value. That's a nice little C compiler kind of error. So something's on the left-hand side of an equal operator, and it has to be something that can be modified. So that's line 48 here.
I think you had a constant pointer for output.
That was a copy. Then that was a copy paste kind of error because I deleted the B versus the C for what I was changing there. Thank you. Okay, one compiler error message fixed. This one is concerning me a little bit. Okay, and then line 146 expected a semicolon. Well, if you expected a semicolon, just add a semicolon. Looks like I don't trust the syntax highlighting here. If FEXP of that minus that, I'm just missing a parenthesis probably, right? Or is there one too many? Promising. That's promising. FEXP is undefined. Is it not called FEXP? Mathlib. It's not called FEXP. It's been a while. It's called EXPF. What did I call it? FEXP? So it's called FABS for floating point abs, but EXPF.
What's up with that?
Doesn't seem right. Well, the reason for anything in C is due to generations of cruft that it has to be maintained for compatibility reasons. Okay. It's been a while. Okay, what can I tell you? So at least it should compile. We should get code that does something, I guess. It's going to be wrong still because it's not actually computing vector add. So it's still called vector add. I didn't change the make file. And it's going to, result verification failed at element 0, which it should, right? I mean, what is the verification doing? It's checking whether or not the actual EXPF function gives us the same result as what we calculated in our kernel and whether it's within some certain range. I mean, if we want to pass verification, there we go. now we can pass verification. I mean, if we want to confirm that I got to remake it. Now, if we want to, confirm that our verification code actually, computes and gets through the whole array, that's fine. And the test passed, but that's not a very meaningful pass. But at least, okay, we got all the way through the code. It did launch the kernel. It did return some results. The results, though, it currently returns doesn't have anything to do with Taylor series expansion yet. So, ready for some actual math here, right? So, let's add some comments. So we need to grab x of I, and our goal is to calculate what? E to the x of I. E to the x of I and store as output of I, or as output of I. This approximation works when x is close to that a equals 0. Just in terms of the accuracy, in terms of the number of iterations, that's something you maybe would have learned in a calculus course, but maybe not, and maybe it was many, many years ago, and it's okay. You have to kind of, the hope is that you can go back to the calculus textbook if you ever have to implement this, and you can kind of sort it out after the fact. So around a equals 0, it's referred to as the Maclaurin series, but it's fine. It's our Taylor series expansion of that. And ultimately, because we're doing e to the 0, the rest of the terms kind of cancel out, right? So this kind of scary term where we have to do the differentiation kind of cancels out. X minus 0 to the n becomes x to the n, and then we're doing n factorial. So that's actually all that we're doing. For n number of iterations. For the number of iterations we specify here, we're really just calculating the x to the n divided by n factorial, and we have to do the sum of that. So calculate the sum of x to the n divided by n factorial for n equals 0 to num iters. And I think you're all far enough in your development careers to know, you have to add some mental notes for yourself before you get started. If you don't do that, it's impossible to start, I always feel like. So, okay, maybe these aren't good enough mental notes, but we can get started. When n equals 0, 0 factorial is 1, x to the 0 is 1. So our initial value for x val can just be x of I. And our initial value for calculating the power, the current pow n can be 1.0. Because it to the 0th power there. And then which factorial is something we can kind of just calculate as we go. Start at 1, then multiply by 2, and we also need to keep track of our sum, which can also start as 1.0. So we can actually skip the first iteration if we assume we start with 1.0 for our first term. So j equals 1, we did the first iteration, j is less than num iters, j plus plus. We then have to calculate the next term of x to the n. Fine, just multiply by the value which we grabbed of x of I. Calculate the next term of x factorial. So what do I call that? N fact times equals j, starts at 1, multiplied by 2, multiplied by 3, multiplied by 4. And then calculate the sum of stuff. Calculate the sum, x pow n divided by n fact. And then output of I now is just then equal to sum. This approach looks a little simplistic. It really only works because we're doing e to the x. So we don't actually have to calculate any derivatives. The derivatives are kind of itself. So that's not a hack. That's just what we're doing for this example. It also easily works. We don't have to calculate e to the x at all because we're doing it around a equals 0. All of our inputs are around a equals 0. They span from -1 to 1. So we're calculating e to the x without actually needing to do an exponentiation at all. It's still, I always felt kind of a magical thing, right? Because we're doing value to the n divided by n factorial, and we do that enough times and we get a value that's equal to e to that x value. So I think that's kind of cool. In terms of the parallelization strategy here, at first glance this actually doesn't look parallel at all, right? This looks like a function. If I told you to write a function, it would do exactly that. So there is no parallelization here in this block of code. This is vanilla C code for Taylor series expansion. The parallelization, to the extent you can actually see it at all, is kind of happening here, right? Where also in the actual kernel launch that we have, here is where the parallelization is being kind of specified, where we're saying everybody's running this exact kernel code, they're doing the same exact thing, but we're going to launch it in this block of threads here, and consequently, as we do our little bookkeeping in the beginning to calculate that value I, they're all running the same kind of sequential code, but they're all getting to do that in parallel. They're all taking a different value of x or a different index into the array x. They're all calculating a different index into the output array output, and so it should be in parallel. I have to be honest, I don't have a lot of confidence that this is going to work. Give a quick look over before I run it because there is no easy debugging hooks with this. Later versions of CUDA than what I'm running here can allow you to do printfs and things like that. Otherwise, there's profiling and other tools one can use. Debugging and visibility to design becomes not as difficult as it is for our FPGA designs, but it's a similar kind of mindset where once things are running, it's a bit of a black box and you have to find ways to extract intermediate results to get debug information. Because it's e to the 0, just x to the nth power divided by n factorial. You can start with that. X to the nth power, we just multiply it n times. That should be fine. Factorial starts also at 1.0 for 0 factorial. For 1 factorial, 2 factorial, multiply that. And we add the sum each time. With the sum starting at 1.0 because we're doing 1 divided by 1. What could go wrong? All it's going to do is say that test passed or test failed here. There are a lot of command line arguments going on there, just specifying the particular compute capabilities here. This is all from NVIDIA's SDK, CUDA SDK, and some of the defaults it provides for their makefiles. Yeah, looks all right. If I were to instead take values as my input that were not around 1.0, so the easiest way to just do that would be, from negative 100 to 200, or I think even negative 10 to 20 would, same kind of span of values, but now from negative 10 to positive 10 here. I would not expect that to pass because this Taylor series expansion is only stable around the point A that you specified, and now we're no longer that close to the point A. And it failed on the very first element. But this version at least kind of sort of works. So we'll leave that there. So let's talk about the thread organization, because that's the part that is kind of just fuzzy and not really specified as of yet. So there is this important concept, and when you're doing CUDA, as we saw, the actual C or Python or whatever you're writing, that code isn't any different. If you can follow the arithmetic or the logic or the math of what you want to do, that code doesn't really change. What does change is how from the very beginning, your first part of the problem-solving process for a GPU compute application is, what is my thread workload and my parallelization strategy going to be? I did talk about that on Tuesday, that itself is a much bigger topic, right? That is whole separate courses on parallel algorithms and how to approach problems and think about how to partition them in parallel methods. So we'll go through a couple examples, but they're going to tend to be pretty facile from that perspective. That very coarse-grained parallelization is what we will be doing. But in doing CUDA coding, we do have to think about what is my resulting thread organization going to be. That is a limitation driven by architectural design decisions. Although, just like in graphics, the architecture and the software capabilities kind of co-evolve. But here, when you ask the question of, why is there this particular limit on how big our block size could be, the answer is generally there's some hardware resource that there's a register that's only this many bits wide, and if they made it one more bit, that would lead to all sorts of downstream changes in terms of what type of architecture would require. So there's some fundamental hardware limitations kind of restricting what we can do from a software parallelization strategy. But we have to get a good handle on what that actually could be here. So a couple of the terminologies you want to kind of keep in mind here is we have this thread hierarchy where we have an initial array of threads that are formed in a block. So there's a block of threads. That's been shown in this diagram here. This is a two-dimensional block of threads. They look kind of weird, these little squiggly threads here, but those are a two-dimensional block of threads here. You can have a one-dimensional block, two-dimensional block, or a three-dimensional block. That is just your first decision you're making. I have a certain number of threads, and I'm going to declare a multi-dimensional, potentially data structure to represent what those threads are going to be organized and how they're going to be laid out. I think it's a totally valid question to ask right now to yourself or to me. This is 12 threads here. It's a 3x4 block of threads. Why 3x4? Why not 2x6, 4x3, 12x1? There isn't a specific answer to that outside of the context of a particular application. And it may also be that 4x3 would have worked just as well, or 2x6 may have also worked just as well for an application. So don't get hung up too much on that. What tends to often be the case, although for really advanced applications there's some more subtle strategies going on, what tends to often be the case is your parallelization strategy tends to at least some extent map the dimensionality of your data. So for this example where it's n by n, and that's just given in this example for the matrix addition, so we have kind of a square block of data, if you want to think of it that way, that we're adding together. It probably then makes sense to have kind of a square block of threads in your hierarchy. It's not a requirement, but that's kind of a natural one-to-one mapping between data dimensionality and thread parallelization dimensionality. But otherwise, and this is meant to be a very rhetorical question, there is no right way to organize a grouping of our threads. But just to make sure we're on the same page with regards to the terminology and later some of the restrictions here, you have an array of threads that are formed in a block, 1, 2, or 3 dimensions. You then also specify a number of blocks that are going to be in a grid, which is also 1, 2, or 3 dimensions here. So when I mentioned this is a potential six-dimensional kind of layout problem, it is. It's hard for me to think of good six-dimensional, examples, probably for such that which the data also has that dimensionality. Oftentimes the challenge from the programmer's perspective when doing CUDA is how do we keep the GPU kind of full and busy and always doing work? And it turns out there tends to be kind of a bit of diminishing returns, but to get to that point, you have to have a sufficient number of these blocks to make sure the GPU is always doing some work. Because the thought is, if the GPU is always as busy as it can be, you're probably doing a pretty good job in terms of extracting some parallelism back out of your application. So the answer isn't always necessarily why 3x4 versus 4x3 versus 2x6 for your dimensions of a block. It oftentimes is more, how do I get 64,000 threads on from this particular kernel? What layout and parallelization strategy allows me to get to that number? Because I did some analysis and it turns out if I have less than that, part of the GPU isn't busy for certain percentages of the time, and I don't get good speed ups when that happens. So threads in a block, blocks in a grid. It is, at least in this example, already kind of a four-dimensional layout of our threads. Because we have our grid that we specify, which is two-dimensional, and then in each block, which each block is going to be identical in terms of its dimensions, you have upwards of, in this case, 2 dimensions here. So you can have a single-dimensional grid where you have one thread in one block. That's fine. You can have upwards of 6 dimensions where you have a 3-dimensional block, XYZ, and then your grid is also of dimensions XYZ. And that's a lot of dimensions. And I can't even draw it, right? But certainly that somewhere anything in between is valid for that. If we go back to the vector add or Taylor series example, syntactically we can still talk about what that means in practice, but we can now kind of visualize what our thread layout looks like for that example. This caveat's important, and we'll talk about this again, that when we talk about a kernel, it's the grid that gets executed. You specify, here's the amount of work I want to get going on my GPU, and it's one grid at a time. Yeah, Andrew.
So usually when you're writing like parallelized code like this, are you writing for a specific architecture? Because they're all NVIDIA GPUs, but they might have like different.
And it really depends. And let me talk about that a little bit because that is important. And I think the answer is kind of sort of. It's a fuzzy answer because part of the design criteria for CUDA is it was meant to be somewhat device independent, and it can be device independent. And the mechanism, just to jump ahead a little bit here, and I'll come back to this in a second, is in theory you have something like this diagram, this visualization I'm showing here at a very high level, where your application specifies a grid of 8 blocks. I don't even talk about the dimensionality here, but you have 8 different blocks you want to execute. And perhaps today it's running on kind of a testing device that you have in your workstation or in your laptop, and consequently the blocks are going to get parallelized across 2 NVIDIA streaming multiprocessors on the GPU, and then later you push it to another device that has twice as many streaming multiprocessors. Then in theory you get more performance because there's more blocks that can get executed at any given time. In practice though, it does seem that well-written CUDA applications are kind of hyper cognizant of what type of device it's running on, and CUDA provides a lot of hooks for that. That what you can do is you can query device compatibility, device capability I think is the right term, but it's also compatibility with what version of CUDA it can support, and consequently you can do different things in your code. If this is a 2020 device, you can do this. If it's a 2021 device, you can do this, and so forth. So the answer is yes and no, I guess. It should be able to work. This code should work on old device and new device and get some sort of performance out of both. In practice, there tends to be a lot of setup code that really does carefully query, what device am I actually running on here. Let's mention, this restriction of what happens in a block. When we talk about our parallel applications, very few are going to look like our vector add or our Taylor series, in which the way we did this parallelization strategy, each thread can be, completely blissfully unaware of every other thread. There are very few applications that truly can be parallel. There's very few interesting applications that can be truly parallelized in that sense. If you hear the term embarrassingly parallel, that's what that's oftentimes referring to, where it's truly split it up as many times as you want, and there doesn't require any cooperation or synchronization. Real-world applications that may themselves be amenable to parallelization strategies tend to only be partially parallelizable. And you may have learned about, Amdahl's law in a computer architecture class, and that's super relevant for parallel computing purposes, in which we really are limited by the percentage of our application that can't be parallelized, right? If we can parallelize 90% of our application, it doesn't really matter how much we can parallelize that 90%, our performance is ultimately limited by that other 10% that we're not parallelizing. Real world applications, if you can get 90%, that's wonderful. Maybe if it's only 50%, it's probably not even worth all the effort, right? But long story short with that, real world applications have some synchronizations that are required, that they are parallel for certain stretches, and then they have to kind of synchronize and make sure that all the threads have caught up with each other before it can go on to the next stage. This is a design decision in the CUDA world by NVIDIA, such that only cooperation between threads that are in an individual block is allowed. So there are some primitives that allow you to either share data or locally synchronize between threads. None of the examples we're showing today do that, but it's limited to threads in a single block. When we have different blocks then in the same grid, they are meant to be truly independent of each other. There is no way to check from any thread in block 00 to check how block 1, 0 is doing. Not only is there no mechanism in software to check, you actually have no guarantee about the actual order in which they're executed. Presumably it kind of goes, left to right, top down, probably right, it gets laid out in some reasonably smart pattern, but beyond that you don't really know. So these blocks are then completely independent of each other, no real guarantees about what order they execute in, to what extent they are done with their computation. Only within threads in a single block can you have some level of synchronization here. And that does dictate part of the answer to this question of how you would organize 1024 or any arbitrary number of threads. It doesn't give an answer for the general case, but in a specific case, as you start to think about your problem, you can think of it in terms of what parts of my task require some synchronization. All that has to fit within a single block. What parts of my task are then embarrassingly parallel? Those can be different blocks laid out in a grid. If we look at the vector add, or now our Taylor series example here, it's doing a little bit more math to make sure there's not too many threads here, but first specifies there's 256 threads in a given block, so that's a single dimension, that's an X dimension here. That's the layout of threads per block, and then to get effectively a single thread per element, it takes that value of 50,000 and divides by that 256 to say, here's how many blocks you're going to have in your application. In our case, it doesn't matter as much because everything is completely parallel with each other, but there's also some hardware limits to how big a certain dimension can be. So this is just one approach to laying out effectively 50,000 threads for this application. For other applications where you do have some parts that have to synchronize with each other, you have to think about that first, and then you worry about how you can lay out those different blocks in your grid here.
Where in the code do you actually specify the size of the two-dimensional?
Well, this example kind of stinks because it's just one dimension.
Oh, this isn't the...
Yeah. So it's not that great because this is just a single row of threads in a block. So it's 256 by 1, I guess. And then a single row of blocks in a grid. So whatever 50,000 divided by 256 is, that many blocks in our grid. So otherwise, kind of similar to what we have in our GLSL, I think it's called a DIN3. Yeah, there's built-in variable types to support laying out an X, Y, Z for what you want those dimensions to be, and your launching would look like this. I do have the matrix multiplication. Let's undo that before this doesn't compile again. I do have the matrix multiplication example. I haven't looked at it relatively recently here, but that should be doing a little bit of that. And it is kind of specifying, in this case, it is kind of a three-dimensional layout here. We don't have to worry about all the syntax for this yet. We're going to go into this example in more depth, but it's specifying where in the actual CUDA launch is going to be near the very bottom here. Grid dimensions, called threads, but it's really block dimensions here. And we're specifying, here's what our block size is. In this case, is a 2-dimensional thing. And here is what our grid size is. So here is launching. This would be a 4-dimensional layout of threads that we have in this example here. So architecturally, let's dive back into that. We have these concept of streaming multiprocessors. Depending on which generation you're looking at, they're called SMs or SMX, and they operate on blocks at a time. The multiprocessors themselves, the SMs, are composed of the individual stream processors, also called CUDA cores. Kind of, as I mentioned, that term's also starting to go away, and they just refer to them as just individual compute units, be they floating point of different types or special function units. The fundamental limitation is still there, that given a GPU composed of multiple of these SMs, a given block in your application in CUDA can be scheduled onto any GPU multiprocessor. You don't really specify. You say, I have this many number of blocks in my code. It has some dimensionality, but ultimately there's a set number of those blocks, in this case 8 blocks in this example, and they get launched onto any GPU SM multiprocessor at any given time here. So one possible layout of this grid onto device 0 would sequentially in time maybe look like something like this, where I would partition a certain number of blocks onto SM0 and a certain number of blocks onto SM1. And we'll talk about why there's going to be limits as to how many you would launch on any given SM. There's physical resource limits that prevent us from launching all of them on one at any given time. And that would be our parallelization strategy here. It's not to say that you're limited to a speed up of 2, but you would be able to launch a certain number of those threads, and it'd be the CUDA scheduler, the runtime, that would determine how that would happen. On a different device where you potentially have 4 SMs, as we just talked about briefly, perhaps the layout in time looks something like this, where we can still fit 2 blocks at a given time on an individual SM, but because there's more of those SMs, now we're maybe fitting all 8 blocks at once. There's presumably some kind of ready queue associated with this, where for in this example, we were able to fit the first 4 blocks. Once one of those blocks is completed, meaning every thread has reached the end of its execution in that block, then we go and we launch block 4, then 5, then 6, then 7 on that SM. So presumably, all else being equal, this example is roughly going to be, this device will be roughly twice as fast in the application as this one here. But we can't even necessarily say that with any confidence, because it's not the case that having twice as many threads or doing twice as many things in parallel means we have twice the speed up. It depends on the amount of synchronization, depends on what other bottlenecks there may be in the application. But the idea is, in general, when writing CUDA code, you have a certain number of SMs on your device, and the number is not 2 or 4, it's quite a bit larger now. And the goal is, can I keep them all full? Can I make sure they at least have enough threads going on them at any given time that those individual cores aren't sitting idle? Because then you're not presumably taking advantage of the hardware you have in front of you. If you do need to cooperate between every thread in your application, there's lots of different ways you can do it, but the most common approach is to have just separate kernels at that point. And then separate grid layouts, separate block layouts as well, where if you do have, one way to think of this would be sequential or serial parts of your code followed by parallel blocks in your code, you would actually do those serial parts kind of independently of the kernel launches. So host side code does some work, does some setup, some arithmetic, launches a parallel block of code that does as much as can be done in parallel. We actually need to combine all those results together and do something with it. That would then likely be the job of the host side then to kind of collect results, combine results in a serial branch, and then it would go back off to your parallel via multiple subsequent parallel invocations of different kernels. That's a pretty common approach. A lot of the textbook examples just do a single kernel at a time because that's kind of enough for us to handle. But we could, if we had wanted to, do a vector add of, e to the 0 plus e to the 0.5 or something like that. We could have done 2 kernels where the first one's doing the Taylor series expansion. Maybe we do it twice, and then we add those 2 results together via subsequent parallel kernel launches. It doesn't have to be just a one shot of just a single kernel launch per application, but that's our primary whole system synchronization point, which is you launch the kernel. We oftentimes need to wait for the entire kernel to be complete, every thread to be complete, and then that's our synchronization point. Then we do whatever. We can launch more kernels, we can collect results, we can do whatever needs to be done on the host side after that fact. let's talk about memory. These are architectural design decisions that do impact the programming model. I would argue that the same architectural design decisions impact on conventional CPU architecture how we write code, but oftentimes that gets abstracted away enough that we don't really need to think about it, right? When you are writing code, you oftentimes are not thinking about cache. I mean, some maybe embedded or other really performance critical example, maybe you do, right? Hey, I'm not getting quite the performance I need. Maybe I can do something better from a cache perspective. Or, the registers, you may say, well, that's really the runtime's job these days to kind of do register management for me. But if you're finding you're spilling the memory too much, you may then decide to find ways to minimize the amount of registers that are being allocated. When writing CUDA code, we can oftentimes ignore those details, but it can become the limiting factor in terms of how many threads we can launch at any given time, how busy we can keep the GPU. So there's going to be a register file per SM. It's going to look a little different than a conventional CPU register file. There is also, as was added when we had unified shaders, a shared memory block per SM, still relatively small. We're not talking, like a modern AMD CPU can now have a 64 megabyte last level cache and even bigger, these crazy large caches. These type of shared memory blocks still tend to be very modest, like 512 kilobytes or something like that. So there's an amount of shared memory for the individual threads to coordinate and cooperate with in a block. There's a reasonably large sized register file, and then everything else has to go off to off-chip memory. So your global, your graphics DRAM, your off-chip memory where everything else is going to be potentially stored. You still have things like a cache to store constants. If you need to do texture lookups, there's still access to not really a separate physical memory, but a unit that allows you to do texture lookups. But from the general compute side, this is kind of your new programmer's view of memory of what's happening in the system. You have registers, you have shared memory, and if that's not sufficient, everything else goes off into global memory here. In our vector add example, there were registers, we weren't really necessarily looking at them. Everything else was just being allocated in global memory here, and we're just doing that via a function call that does something kind of similar to what our conventional malloc does, but it's our special CUDA malloc. Allocate memory on the device, give me this many bytes, and report back if there was an error or not. Here's an example device, the G80 that we already talked about, has 128 total streaming processors and 16 streaming multiprocessors. So quick math is that's 8 SPs per SM here, or 8 CUDA cores per SM. Current generation Hopper, and that's not actually a picture of a Hopper. I couldn't find a good chip layout of a Hopper. That's an Ampere device, but still a pretty high-end device. That is 144 SMs and 18,000 plus streaming processors with a higher ratio of streaming processors per multiprocessor. The rhetorical question is, does this change how you want to write code? The answer is probably yes. I mean, if you're targeting a very old device with very limited resources, probably your application would be different than when you're targeting the latest and greatest device. But in terms of compatibility, applications that were written for the G80, which is getting pretty long in the tooth at this point, will still work. Will still work. It just won't take great advantage of what the hardware has available to it. It'll be using a very small amount of the modern chips here. I mentioned that to some extent after this initial kind of architectural revolution of doing unified shading and GPU compute, in my just personal professional opinion here, the main evolution has been more of a VLSI and semiconductor advances than it has been architectural changes. Just looking at the transistor count, it's kind of mind-boggling in terms of 681 million transistors is still quite a lot if you ask me, versus 80 billion, roughly 80 billion transistors. That is a very large number of transistors on a particular chip, and all fitting within some thermal envelope that is reasonable given a certain cooling system and power supply is pretty amazing. In terms of architecturally what's happening though, we start with this architecture. This is kind of the textbook G80 architecture here. We saw a different version of this on Tuesday. These are our SMs, these kind of sub-columns here. In between it are our the smaller boxes. Those are our individual kind of CUDA cores. You can really just think of them as individual functional units that we have instructions that are going to target here. The rest is what we talked about on Tuesday with regards to supporting both kind of the graphics interface to the same hardware as well as the more general compute interface to that same hardware here, right? These are our render output IP cores here. We got our rasterizer going on right here to generate the fragment work. And then when we zoom in on an individual SM, it is different than your CPRE 381 style pipeline. It's not that different in terms of what's going on here. There is additional hardware of the type you will learn about more in like a CPRE 581 of how am I scheduling multi-thread, so multi-threaded issue. How do I get 32 or maybe 8 threads per cycle off at a given time here? I have an instruction cache. Instruction caches here are going to perform extremely well in terms of the hit rate on those caches. Every thread is doing something different. They're all executing the same instructions, right? They're all using the same instruction memory. You should get very good hit rates of 99-point-something% in your instruction cache here because it's all executing the same kind of code. This is our constant cache that's going to store some of those constants we may have in our shader or CUDA code here. And then while it's not showing the actual pipeline layout in terms of muxes, you can ultimately think of these as your vectorized floating point unit here. Allow me to do 8 floating point adds or 8 floating point EXPF implementations at a given time, floating point multiplications at a given time, and then the rest of it is just keeping track of, for my threads that I'm scheduling, where are they in terms of their execution in the code. The reason we need to even do that level of keeping track of where things are not with regards to executing things like floating point addition and floating point multiplication, is when we want to then access our global memory or access off-chip memory here. We're not showing the cache, but there is then your data cache as well. If you're then going to have this group of threads, and they're all executing this same code here, in general, they are going to be able to execute in lockstep for this. There's no reason they can't. They're all using the same, following the same steps. They all have the same instruction memories. They all can kind of keep in lockstep with each other. The challenge actually becomes in when we access memory here. Now they are not necessarily in lockstep with each other. They're still doing the same thing, right? They're still each calculating a value of I. They're getting a different value of I. And then they're doing a load based on X of I and later a store based on output of I. So they're still in lockstep in terms of the instructions they're executing. But the reason we have to actually manage our threads and keep track of where our threads are in terms of their execution, well, you tell me. What happens here? Why does this become a challenge for keeping our threads kind of coordinated with each other and running in lockstep? When we do X of I, it's not quite shown in this diagram. It'd be nice if it were. But when we execute X of I, well, what is this, right? This is probably a load instruction, right? I mean, and if you look at your PTX kind of virtual CUDA type assembly, it looks very much like MIPS. There's nothing new under the sun with regards to assembly languages and interfaces there. Very MIPS-like, load word style instruction. Given a base address, given an offset constant, and a register to store something into. Assume, for sake of argument, this is a single load instruction, because again, I think it should be, and it can be a single load instruction that every thread is running in parallel. Why is it potentially an issue that after this instruction, your threads would no longer be synchronized with each other? What could happen?
Some of them could hit a cache and some would miss.
It's absolutely the case, right? We don't know the state of our cache. We don't know which of those loads are going to hit in the cache, which ones are going to miss in the cache. And as part of the design trade-offs of fitting more computation on device and fitting less cache on device, I said for the instruction cache, hit rate should be extremely good because they're all running the same instructions. There's not this huge macro executable that they have to kind of swap out different regions of the cache for. There's no fighting there. But for accessing global memory, there's also still a relatively small L1, L2 cache hierarchy. Much less chip real estate in terms of your 80 billion transistors is spent on cache here than in the equivalent large-scale CPU that we have here. So it's actually going to miss in the cache quite a bit. But will all threads miss in the cache? Will some of the threads miss in the cache? We can't actually guarantee any of that, right? Because we have this layout of threads in a block, blocks in a grid. We have very little control over our actual ultimate access patterns here. what values of X of I are going to be fetched at any given time. We have very little fine-grained control on. At that point, now we have some of our threads hidden in the cache, some of our threads missing the cache. Now they're no longer aligned with each other. And we do need special hardware to keep track of where each thread is at any given point in time. It gets simplified somewhat in the CUDA implementation underneath the hood, in that we logically group threads into this batch of 32 threads at a time that's referred to as a warp. So if you've heard the term warp execution or warp divergence, that's what that's referring to. We don't specify anything about that block of 32 when we write our CUDA code. There's no concept of a warp in CUDA itself. But underneath the hood, in terms of how our work is getting scheduled, it's an individual block that gets scheduled, but the individual instructions get scheduled 32 threads at a time that stay coalesced with each other. That's what's referred to as a warp. That somewhat cuts down on this issue because it's not arbitrary accesses. Presumably, the 32 threads will have some spatial locality in terms of what they're accessing in memory, so cache performance should at least be kind of predictable based on that. But we do need then that hardware to kind of keep track of our work as it's going here, because the other trade-off that tends to be made is in doing the DRAM for graphics architectures versus for more conventional general purpose workloads, we do tend to trade off latency for increased throughput. So you will tend to see relatively small amount of data cache, as well as relatively small amount of instruction cache, and DRAMs that have high throughput but relatively long latency, 600, 700 plus cycles of latency here. So in terms of what is the right number of threads for our application, kind of hinted at that, right? Our goal is to have enough threads so that these SPs always are doing some math, right? If not our SPs, then our special function used for sine and cosine and things like that. We're keeping them full, because that's as good as this architecture can do, right? You have 128 SPs, you have 18,432 in the latest and greatest 80 billion transistor chip, and really the best we can do in terms of using parallelization in that architecture is to have 18,432 interesting things going on at any given time in terms of computation that's happening. Can we keep them all full? The fundamental challenge is not that, okay, just specify 18,000 threads and we're done, is that these threads are not always going to be doing interesting work at any given time. We're making the trade-off of having way less cache and higher latency memory for higher throughput and having more real estate dedicated to functional units, but then the trade-off is, okay, we fetch X of I, and now maybe half of our threads have to sit for 600 cycles. We need way more than 18,000 threads, or 128 threads in this example, to keep 128 CUDA cores busy at any given time. Because a long period of time, they're going to be sitting and waiting for memory, and that is the CUDA approach. Can we provide enough threads so that even if a certain percentage of them are always sitting around idle and waiting for memory to resolve the request that we put for a cache miss, there's enough threads sitting in the queue ready to go that we always have an SP doing interesting work at any given time. So let's leave things here for today. We'll pick it up on Tuesday. There's a lot more we need to cover with regards to this, but that's the mindset. Go back to that kind of rhetorical question of like, how do we launch 1,000 threads or threads? How do we organize 1,000 threads? And know that it is a rhetorical question. There isn't an answer. But part of the answer is, how do we get enough threads into our system so that for whatever hardware we're targeting, we're keeping it busy at all times, knowing that even if we write something that seems relatively straightforward, anytime we access memory, kind of all bets are off for that individual thread's perspective. It's going to have to wait 600 cycles to get X of I. We better have enough work to keep the processor busy for those 600 cycles, or we're going to feel that full latency. It'll be as slow as any other cache miss we would have in a given system. Let's leave things here for today. Keep chugging along on your projects. I'm excited to see some demos coming up here, and we'll pick up right here.